Our next speaker is Wang. He's going to talk about user-customizable transpilation of scripting languages.
Oh, okay. So, welcome to the last talk of the day. I'm Wang, a PhD student from National University of Singapore, and this talk is about automated code translation for dynamic typed scripting languages. And this is a joint work with my colleagues. So first, why do we need code translation or code migration? So one reason is that programming languages are evolving over time, and some languages that are popular 10 years ago are being replaced by newer languages. And people want to move to languages with better features and supporting ecosystems. Another reason is that people want to share the code with developers in other application domains. So this is similar to natural language that we might want to translate a book from one language to another to share the knowledge with more people. In code translation, where we have some libraries in one language, we might also want to port it to another. But one big difference compared to translating in natural language is that unlike books, that the code repositories can frequently bump into newer versions. So let us look at a motivating example. So here, Bob wants to develop an app for a serverless platform, and he has some code written in Python that he wants to reuse. But the serverless platform only supports JavaScript runtimes, and they require the developers to write applications in JavaScript. So Bob wants to translate his existing Python programs to JavaScript. The details of the code here is not important, but notice that the program 1 uses third-party APIs provided by a library called NumPy, and the second program uses only built-in APIs from the Python standard library. So Bob wants to find automatic code translators to help him instead of doing the translation manually. He found a popular Python to JavaScript code translator on GitHub, which claims to support Python 3.9 to JavaScript code conversion, and we call it translator G for convenience. Bob first tried to use translator G to translate program 1. However, the translation aborted with an error message. It failed to translate the third-party dependency library NumPy. But Bob is not interested in translating this third-party library. Since there are existing many libraries in JavaScript that provide similar APIs, he expects the translation to leverage the libraries native to JavaScript, such as TensorFlow.js or Math.js. So Bob then tried to translate the second program using translator G. And this program doesn't use any third-party libraries, so the translator G can successfully output a translation. But if we take a closer look, you can see that this translation actually imports hundreds of functions that mimic the Python standard library. So the translation seems to be like doing the emulation of the Python runtime in JavaScript rather than express the same program in JavaScript code using the native APIs. The translation is also verbose with nested loops and temporary variables. So what kind of translation that Bob is aiming for? For the first program, P1, if Bob could do it himself, he would be using some third-party libraries that provide similar functionalities to the NumPy library in Python. For the second program, P2, he would prefer a translation that use native JavaScript APIs while written in a newer language standard of JavaScript, such as ES7. From Bob's experience, we can find that the code migration problem involves many factors. So first is that users have their different preferences on the generated code. Second is that there are millions of third-party APIs available to a language. And the third, popular languages are evolving at a fast pace. These factors give us two observations. First is that there are usually multiple ways to translate the same code. And the second, it is difficult for a translator to generalize to every program. Thus, maybe a better solution to code migration is to find better ways to build specialized code translators. For example, instead of building one translator G trying to solve all the translation tasks, can we build specialized code translators with low cost that perform well on specific tasks? So here we have several research questions. First, how much human effort is needed? And second, can they perform better than general translators? And third, can they work for various styles of code? So in this paper, we are making the following contributions. First, we propose a user-guided and test-driven design for building task-specific code translators. And second, we implement a prototype named DuoGlot, a user-customizable translator for Python to JavaScript code conversion. And third, we compare the DuoGlot with existing translators on 3 benchmarks, and it can translate 10 to 20% more programs correctly with low human cost. So now let us look at the workflow of using the DuoGlot code translator. So given a rule set, DuoGlot will try to use these rules to come up with a candidate translation. The translation will be checked by a tester. If the translation passes test, the candidate translation is output as a translated program. Otherwise, the error message will be fed back to the DuoGlot translator. The translator might keep trying to find candidate translations, and when they fail to find a new one, the error information and the partial translation is provided to the user instead. The user looks at where the translation gets stuck and write code snippets that demonstrate the translation of that piece of code. The code snippets are then sent to the rule inference, which will synthesize a translation rule and add that to the rule set. The loop on the left is a machine loop, which is a frequent case and is fully automatic. The loop on the right is a user loop, where the user intervenes only when the translation is stuck. The code translation process has 2 outputs. One is the translated program, and the other is a rule set that produces the translation. Notice that DuoGlot is differ from traditional code translator in 2 aspects. So the first is that the translation rules are synthesized from user-provided code snippets. And the second is that the translation process is iterative and automatically leverages test feedback from unit tests. For Bob's scenario, for the first program, he needs a rule set that's translating NumPy API calls to Mass.js API calls. And he can either create one himself using the code snippets or get it from other users with similar needs. With this rule set, he can automatically translate program 1 into a JavaScript version that uses Mass.js as a third-party library. Alternatively, if we want to use TensorFlow.js instead of Mass.js, he can choose another rule set to produce an alternative translation. For the second program, Bob can use a rule set that translates NumPy to JavaScript ES7, which is a relatively new language standard. With the rule set, DuoGlot can convert the program into idiomatic JavaScript code that use language features available in this version of JavaScript language. For example, we can see the use of const, map, exponentiation operator, arrow functions, etc. Now let's look into some technical details. So first question is that in the DuoGlot user loop, how do we create translation rules through user interaction? Here is a step-by-step example. So assuming that we want to use DuoGlot to translate this Python program, and the initial rule set is not comprehensive. So DuoGlot finds that there's a missing rule for the list comprehension on line 2 and asks the user to provide a translation rule. The user will provide 1 or 2 pairs of example code demonstrating the translation. Notice that different users may want to use different language constructs and APIs. The code snippets is then processed by a rule inference module in DuoGlot. The rule inference module will then infer a rule that can perform the translation demonstrated by the code snippets, and then the rule is added to the rule set. The rule inference works purely at the syntax level. First, the code snippets are parsed into fragments of ASC trees. And then it will try to extract common patterns from the 2 Python examples, and it will do the same for the JavaScript code snippets. The extracted pattern is a partial ASC tree with holes in it, and then it will perform an edit distance comparison, trying to match the holes between the source pattern and the target pattern. After that, the patterns will form a translation rule. And the Q here means that the partial ASC to be translated, and this rule will reduce the translation of the list comprehension into the translation of the expression, the loop item, and the iterable. Now, assuming that we have enough syntactic rules synthesized from user, the second problem is related to the machine loop of DuoGlot, which is how do we choose the correct compositions of those syntactic rules? So this is a problem because that for one piece of source code, many rules may apply. So not all rule compositions result in correct translations. So for example, in the first column, we can see that some translations performed by blindly applying syntactic rules that each of them seems to be correct can result in syntax errors. The second column shows that there are multiple ways to translate if X in Y, depending on the runtime type of Y. So here, which rule to apply depending on the semantics and context. But we do not want to burden the user to specify the applicable conditions of each translation rule, as that will be like writing the compiler. Thus, how do we figure out which rule to apply when there are ambiguities? The method we use is to leverage both grammar and unit test feedback. For example, first we test the translated code, and the tester produces an error message saying that there's an error on line 2. Then DuoGlot will find out the rule application that produces line 2. It will retry that part with other rule combinations that are valid according to the grammar, and also trying to fix the semantic error. And this process is done automatically. So here is a 5x slowdown of DuoGlot machine loop, resolving ambiguities in rule composition and automatically fix all the translation errors. The translation is done when the translation passes all unit tests, and the user can hover on a piece of the translation to see the mapping to the source code and the rule applied. Notice that the translation process is fully explainable and controllable. This is also an advantage over code translation using language models. To summarize, DuoGlot is a customizable code translator with the following design goals. So first, it is low-effort customization achieved through synthesis of rules using code snippets. And second, it is automated rule composition that is guided by the grammar and the unit tests. We evaluate DuoGlot on 3 sets of Python programs with unit tests as our benchmarks, and each set has programs with different sizes and styles. So GeeksForGeeks programs are mostly old-style Python 3 procedural code, and the LeetCode programs are a relatively new set of programs collected from GitHub for a programming contest platform, which is mostly written in modern-style Python 3.9. And CTCI programs are also old-style Python 3 programs, but using object-oriented style. So we compare DuoGlot translator with existing compiler-based translators and a large language model. The most popular and well-developed compiler-based translator is Transcript, which is written in more than 30K lines of code and has around 3K of stars. This chart shows the number of programs that passes unit tests when using all these code translators. It turns out that the DuoGlot performs better than other approaches when equipped with a rule set with 142 rules. So this chart shows the human effort and the number of successfully translated programs for the GeeksForGeeks benchmarks, which has 700 programs in total. As more and more rules are added, the number of programs that can successfully pass the unit test is increasing. It turns out that for this specific code translation task, the human effort to create up to 142 rules is 360 lines of code snippets in total. And notice that this amount of effort is far less than developing a general translator, and also the DuoGlot surpassed the general translator when the number of rules reach 100. We then reuse those 142 rules for other benchmarks. So for example, we tested on the LeetCode. At the beginning, this set of rules cannot translate any programs, and because the LeetCode programs are mostly written in like a newer version of the Python language. But 2 of the 3 compiler-based translators have the same issue that they just cannot support the latest APIs and type hints in the newer Python language. But however, for DuoGlot, this is not an issue like after adding 16 rules, it is able to translate more programs than all the other approaches. And as we keep adding more rules, the number of successfully translated programs keep growing. We also observe the similar for the CTCI benchmark. We can see that DuoGlot can easily adapt to those different styles of code and language versions. So in conclusion, we implemented a prototype translator named DuoGlot, a user-customizable translator for Python to JavaScript code translation. We show that we can build task-specific code translators that perform well for the specific task with relatively low human cost. And the user-customizable translator can adapt to different styles of code. The future work includes designing more expressive rule language so that less rules are needed, and we can also consider synthesizing translation rules using language models. The rule composition can also be improved to leverage static and dynamic analysis to reduce the number of retries. And thank you so much. I'm happy to take questions.
what is, in your approach, that connected with Python and JavaScript? Like, if it's rule-based, if I wanted a translator from Python to Ruby, will I have to change any of your code, or I just need to write my own rules?
Oh, I see. Yeah. So there will be minimum change to the system because currently we have it is based on tree-sitter. So it has a pretty printer based on tree-sitter, and we currently implement that for Python and JavaScript. But with a pretty printer for the Ruby, we are able to basically translating between all these three languages.
So, thanks for the talk. I guess the question that probably a lot of people have is, I guess Python and JavaScript in this case have no types. So have you considered sort of extending how you might extend the technique to handle sort of type languages? And I guess also present to this particular session earlier on, we had a talk about translating C to Rust. So do you think that aspects of the borrow checker might complicate, or ways in which you might mitigate around that? Thank you.
Oh, yeah, thank you for the question. Yes, so for typed language, that is, I mean, using a GC, that might be easy. So that's my opinion, but I haven't tried that. But for C to Rust, that is quite difficult because of the manual memory management issue. So I guess mostly you can get something maybe functionally correct, I mean, if possible, but it's very likely to have memory issues, I guess.
Thanks for the nice talk. Have you thought at all about allowing library authors to provide their own rules? I think it would be very interesting if you could ship a library update that then automatically upgrades all the user code.
Yes. I mean, actually, we try to have something like this so that maybe, I mean, in the future, we might have a library with like similar to git ignore, but we have something like a translation config so that once the source library is updated, you automatically have the translated libraries in other languages. I mean, this is something like we hope to achieve. Yeah.
Yeah, I think that would be very cool.
Yeah, thank you.
Hi, can you elaborate a bit more on how you use the error message to generate the rules?
The error message only shows that the error message basically report why the program translation is stuck. And then the user need to intervene and see where is the error, so that basically maybe it try to fix, for example, line 5. It constantly, like it try many times, but it still cannot fix the error, so that the user will come and see what is happening on line 5 and provide a new translation rule for the statement or expression.
So you only look at which line is from, which variable is from, but nothing more specific than that from the error message?
Yeah, so we're assuming that most of the time the user basically look at the error position, the lines, and I mean, that should be enough, like the type and the variable names.
One additional question is like, what happens if user give you the wrong rules?
Yes. So if the user provide a large number of wrong rules, then the system will have very bad performance because like the retry is very inefficient. But if the user just happen to provide one like a mistake, right, and then later the system can find like this rule is never successfully applied, then maybe the user can consider remove that. I mean, so yeah.
Okay. And one question about evaluation. So the thing is like your evaluation on your tool is human guided. So when you compare against other tools, do you try to let the human intervene with their tool as well?
Sorry, I didn't.
So do you use like human feedback when you compare against your baseline as well, or you just take it out of the box?
I mean, so yeah, that's the difference between the general compiler is that the general compiler you don't need. I mean, the developer of the compiler put in effort, but when you use it, you just like click the button, right? But for the customizable translator, you do need constant intervention.
Yeah, but I assume for stuff like codecs, you can provide feedback as well.
Yes, in codecs you can provide feedback, but you cannot really control it in a way that always control it in a way you want.
Yeah, that makes sense. Thanks.
Great work, Bo. So I'm wondering, since your approach is example guided as well, so is it prone to overfitting, to overfit to the data? And if so, what do you do to overcome that?
Yes. So we cannot prove that there's no overfitting in the translated code. I mean, yeah, so rules can overfit. I mean, for example, in the worst case, you write a rule that only works for positive numbers, And then in your test case, there only exist positive numbers and it's pass all the tests. But yeah, but we think so. This can be partial. So first, we need better unit tests, I guess, to really capture the intended behavior of the program. And at the same time, it also depends on the rule language. So if it's more general, then it might be less overfitting. Yeah.
Thanks.
I just wanted to clarify one thing. So DuoGlot requires a suite of unit tests. So if you're going from like one language to like from Python to a later version of Python, you could just reuse the same suite of unit tests. But if you're going from like Python to JavaScript, does the user have to provide that suite of like unit tests themselves?
Oh, so here actually for all these benchmarks, we did some just basically string replacement to convert to the unit tests. And because most of the time the unit tests are just a bunch of assert equals, and so we basically just doing string replacement is sufficient to convert the unit test, like also make sure it's correct. Because the translation of the unit test is usually much easier than converting the code.
Got it. Okay, thank you.
Okay, last question. So there are features that are not common in both languages, right? For instance, it's possible to get dynamic scoping in Python. They could get right closures with dynamic scoping. What would you do in case if it's not, like, if there's no direct correspondence between one feature in this language to the corresponding feature in the language?
Yeah, I mean, so in the extreme case, we might consider Haskell and Python, right? Then maybe, because if there's too much difference between the two languages, then I don't think like this style of rule language will work. Yeah, maybe we need to find better rule inference languages or in some other technique, or program synthesis, which will be more similar to synthesis, I guess.
Okay. Thank you very much. So that's the last talk of this session, and also last talk of the OOPSLA. So thank you for coming.